Okay, good morning, everybody. Thanks for tuning in. Today, we're very happy to have Leo Stein. He's a world expert in applying general relativity to real-world experiments, and he's going to tell us about gravitational memory and numerical relativity. So take it away, Leo.
Okay, thanks, Dan. Thanks for the nice introduction and for the invitation to have this opportunity to speak. Let me try to once again figure out how to hide these floating meeting controls. All right, thanks. I think you can probably see my screen. Is that correct? All right, so yes, I'm going to talk about resolving memory in numerical relativity and fixing BMS frames for modeling. Actually, I have way too many slides, so if I'm going too slowly, feel free to tell me to speed it up. So I guess I'll go a little bit into the background of what these different frames are, what is this modeling problem, and I couldn't resist putting in this graphic that you see in the middle of the slide, which is the persistence of memory, Dali painting. And if it looks pixelated on the right-hand side, that's because that was intentional. So you should be able to resolve things on the left-hand side, not on the right-hand side. So back in the day, numerical relativity simulations could not resolve memory, and now we can. And I'll tell you what this is about and how we do it. All right, so actually to set the stage first, maybe everybody already knows these things, but in in the back of my mind, I'm thinking about things that are observable. So, the story goes back to 1915 when Einstein gets the field equations for general relativity. And the main prediction that I care about here is that time-varying quadrupoles give us gravitational waves. This is something dynamical. We can try to measure it. And this is what a gravitational wave does to a ring of inertial test particles that start out as a circle. The distances change in this quadrupolar pattern. All right. And then if you let these test masses be the LIGO end mirrors, and you make a Michelson interferometer out of them, and the light bounces back and forth, then you can make a detection of gravitational waves. A little bit of gravitational wave will go through, change the lengths of the arms, change the imbalance of how much light is being canceled at the dark port, and you'll get some voltage out of your photodiode. All right, and then we get beautiful observations like this. Maybe this doesn't look very beautiful to you because there's still a bunch of noise in here, even though this is a signal to noise ratio of like 20 something. But the fact that this was the first thing that LIGO saw, and it agreed perfectly with the predictions, within the observational uncertainties, of course, with the predictions of two black holes crashing into each other, was just beautiful to me. So I had a moment when I saw this plot for the first time. All right, and then of course there are many more observations since that time. So LIGO now routinely detects black hole mergers. Black hole binaries are the dominant signal. So binary neutron stars are of course very interesting, and we would like to learn about dense nuclear matter, but the main signals that come out of LIGO are binary black hole mergers. And so of course we should do as much science with them as we can. Here's a kind of cartoon picture of, I don't remember when I got this graphic, but I think it was before the current observing run started. So there were order of magnitude, like 90 binary black hole mergers in that data set. And now there's a binary black hole merger candidate, like, every other day or something. I don't really know how often it is. Okay, so what do we do with this data? So if you're interested in things like astrophysical populations, you want to know for each merger signal, what were the masses of the black holes? What were the spins of the black holes? Was there eccentricity? Things like that. So you've got to do Monte Carlos on the data and do some parameter estimation. And so part of this problem is, so you need good models, right? So I'm going to be talking a little bit about modeling these signals. And because these Markov chain Monte Carlos take a long time, you need millions of samples. then you need fast waveforms. That's also part of the problem. So we can't just like do a numerical relativity simulation for every point in parameter space. Okay. So let's talk about where these waveforms come from. There's this whole industry of predicting the gravitational waveforms from black holes crashing into each other or in spiraling and then merging. So there's this cartoon from Leo Barak of the parameter space in mass ratio on the horizontal and separation between the two black holes on the vertical. And of course, there's also spins, but that doesn't really affect which of these different techniques we use to simulate to model the waveforms that we get from binary black holes. So at wide separations and therefore slow motions and weak fields, we've got post-Newtonian theory at the top. On the right-hand side, when the mass ratio gets very extreme, you can treat the space-time as just a big Kerr black hole with a small perturbation on top of it. So you do perturbation theory about that non-trivial background. So that's the SMR, small mass ratio perturbation theory, sometimes called the self-force program. But when these two black holes get close together, if they're comparable mass, which most of the LIGO ones are, there's really no approximations that you can make to solve the equations of general relativity. So you have to rely on numerically solving the PDEs on computers. And that's the domain of numerical relativity in the bottom left-hand corner. So all three of these are important for producing waveforms, which then you can do everything else with. All right, so let me try to go through all of this stuff so that I don't waste too much time, because I'll get sidetracked. So there are the analytical techniques that I talked about. So post-Newtonian, small mass ratio. Then there's something called effective one-body, which was initially an attempt to like resum post-Newtonian and turn it into something like the small mass ratio problem. But then the EOB industry kind of took off and said, well, we don't know the higher PN terms. Let's just put in extra coefficients and then we'll calibrate them to numerical relativity. So now EOB is a little bit more phenomenological. So there's the semi-analytical family. So EOB moves down here. And then there's also this thing called phenom, which didn't even try to say anything about first principles. It's just, here's what the waveforms look like, and here's an attempt to have like a simple enough mathematical description that you get fast waveform generation, and we can make it pretty faithful to what we get out of numerical relativity simulations. Notice that all of these, EOB is calibrated to NR, this phenom stuff is calibrated to NR. So none of this works without numerical relativity. So numerical relativity is really the ground truth for the merger. So that's when we know things are correct. Unfortunately, the main drawback is that it's very slow for extreme mass ratios. And that's, basically a scaling issue of, how much resolution do you need when you have something that's very small that you want to resolve? And also how long does the in-spiral take when there's an object that's very small? All of these things make the high mass ratio problem parametrically harder than the comparable mass ratio one. And also when you go out to...
Can I ask a question? There's a lot of high energy theory people using amplitudes techniques to supposedly calculate part of the data for the in-spiral. Has that been useful in the actual experiments yet? Does that fit into this first bullet point that you have? Or?
So I'm very, very far away from knowing too much about what's going on in the amplitudes program. But my understanding is that so far they have basically been able to reproduce all of the post-Newtonian results and, well, all of the conservative post-Newtonian results. I don't know about dissipative stuff. That's a question for somebody who's an expert. And I think that they may have even computed several things that are beyond the post-Newtonian / post-Minkowskian stuff. Again, as far as I know, only in the conservative sector. But I don't think that there's any hope of that program being able to tackle the merger, as far as I'm aware.
Yeah.
But it's very nice that there's now a totally independent way of getting the same types of waveforms as post-Newtonian predict. So besides the fact that they're groups doing post-Newtonian and different formalisms. There's the Lagrangian formalism people, the Hamiltonian formalism people. Now there's also these amplitudes people. So it's a good check on everything.
Okay, thanks.
Yeah. And everybody else should feel free to interrupt me if I say something that's silly or you have a question.
Can I also ask something?
Yeah, sure.
So at extreme mass ratio, numerical relativity is not good, but then we can use the probe approximation or so is there a matching between the two regions, or how do people interpolate between?
Yeah, that's a good question. And yeah, there has been work on this. Actually, what people have been finding recently is that the small mass ratio calculations have surprisingly good agreement with results from numerical relativity if you treat it as an expansion in the symmetric mass ratio instead of Q. They've only done certain types of comparisons, but even for like mass ratios 10 to 1, there's like very good agreement for the types of comparisons that they've done, like total flux or flux in the 2-2 mode, comparing between the small mass ratio calculations and the numerical relativity calculations. And people have tried to build unified models in this kind of surrogate stuff, which is the last bullet point here, where they take inputs both from numerical relativity and from the small mass ratio limit to be able to try to interpolate between them.
Is there a region where you can match, or some techniques extends all the way, or what is the?
Yeah, I think, yes, there is overlap here. And so the calculations from perturbation theory, for some reason that is not really understood, as far as I know, seem to work for, again, only certain quantities, but seem to work for mass ratios, going down to like 10, which is not, maybe 1/10 is small, but it's kind of surprising anyway.
I see.
They still don't work at merger, but for merger you can do merger at high mass ratio with numerical relativity just fine. It's really like the in-spiral part that's extremely inefficient in numerical relativity at small mass ratio.
Okay, thank you.
Sure. Yeah, and I can give you references later if you want. I'll point you to some of the papers that have done this work. Okay, so I think I already mentioned this. There's this final thing called surrogate models. Surrogate models are totally data-driven, so they do take some inputs that are inspired by our knowledge of how post-Newtonian works, the fact that we're trying to model two things going around, right? So to basically get the data to be as compressed as possible, you want to use those inputs, but then you don't try to shoehorn the waveforms into any particular form. You basically just take out as much stuff analytically as you can, and then the rest of it is just a bunch of clever interpolation techniques that can be made as accurate as faithful to NR as you want, and take tens of milliseconds to evaluate waveforms. So that's fast enough for Markov chain Monte Carlo. All right, so I really have to speed up. Here are the main takeaways from the talk. I know I haven't actually said anything yet, but so I will talk about this approach called Cauchy-characteristic evolution, which takes our numerical relativity simulation data and solves Einstein's equations all the way out to future null infinity, which is key to resolving memory. So that's the technical new thing, is actually being able to resolve memory in these waveforms. And then I'll talk about the importance of finding the appropriate BMS frame for these waveforms to do modeling. So there's the modeler's problem. Oh, wow. What is this? Is this part of Zoom that I'm drawing on the slide now? Sorry, I don't know where this came from. And I don't know how to erase it. Okay. Sorry about that. And finally, the applications that I'll mention are remnant properties, modeling of ringdown, this thing called hybridization, and finally the surrogate modeling. Okay, so I think I mentioned many of these things already. Back in the day, the way that you solve the Einstein field equations before supercomputers was just to take advantage of symmetries. And so you study exact solutions that have lots of symmetries like Minkowski and Kerr. And then you do perturbation theory on top of those spacetimes. That naturally leads to post-Newtonian, post-Minkowskian programs, and also the black hole perturbation theory programs. And then finally, once computers came onto the scene, people started trying to solve the binary problem on computers, going all the way back to 1964. And they only actually succeeded in doing in-spiral and merger and ringdown in 2005. That's how long it took. All right, so this was the scare cartoon that Kip Thorne used to try to get people to actually make numerical relativity work through the merger, saying LIGO is not going to work unless we have this waveform part in the middle. Maybe it's some crazy stuff. It turns out to be very simple. It's not this crazy stuff. So that's good. But so what you can see here is that there are three regimes in the modeling problem. There's the in-spiral at the far left. We can use post-Newtonian, post-Minkowskian there. We need numerical relativity for the middle part. And then there's ringdown at the end where we can again use perturbation theory. We can perturb around the remnant Kerr black hole. Okay, so I think I'll skip most of this stuff because I think most of you are well aware. So Minkowski, of course, you can write down the Green's function. Sorry, I'm not a particle physicist, so this is not in the Fourier domain. This is in the position domain, but when you have dissipative processes, this is what we need to do. So you can solve the field equations order by order by using this flat space-time Green's function. And we treat the black holes as point particles, and those are basically just sources, and they interact with each other through the gravitational field. And then you turn a big crank, and then you iterate, and you do a lot of integrals, and you get a bunch of long algebraic expressions. So, this was already happening back in 1916. This was, basically the first thing that people did with the Einstein field equations. And you can get this interaction Lagrangian after you integrate out the fields, get the motion of the bodies, and you can also predict the waveforms. So, a lot of PhD students and postdocs do a lot of integrals, and you get big expressions like the one at the bottom of the slide, which is just a very small part of the waveform. Okay, that's the analytical side of things. Let's see, I think actually there's another slide on this. Yeah, actually, here I was pretending that we didn't take radiation reaction into account. Of course, these gravitational waves that you predict carry away energy that makes the binary shrink. So you have to take into account the back reaction on the binary as the gravitational waves carry away energy. So at 5 pn, the orbit shrinks. The post-Newtonian program is not self-consistently at the 5 pn order yet. So all of the calculations so far are, doing things self-consistently, solving these integrals. I think they're up to 4.5 pn now. But then they do this kind of trick where you take the gravitational waves and you compute the radiation reaction from those gravitational waves, and you use that to drive the sources to in-spiral. So it's still not a completely self-consistent picture. In principle, it will become self-consistent, but anyway. I think I might have said something wrong, but hopefully nobody caught it. All right, anyway, so let's move on to the other analytical thing that you can do, the ringdown portion at late times. So, okay, of course, there's still this mathematical question of whether or not the Kerr metric is is nonlinearly stable, but from a physicist's point of view, instead of a mathematician point of view, you merge two black holes, you get something that's another Kerr black hole, but it's highly distorted. And then it will ring down to become a Kerr black hole if you wait long enough. So after the merger, you do perturbation theory about the final black hole metric. So in the 50s, people started doing it with spherical symmetry. So you have a lot of symmetries, you can decouple everything, there's a separable wave equation. So you only have to solve ODEs. And then the Kerr metric, 1963, doesn't have the full spherical symmetry anymore. So you lost some symmetries, so it's not clear how to deal with rotating black holes. But there's some magic in the Kerr metric that I do not understand why it has to be this way. but nature seems to be kind to us. So the Kerr metric, if you use curvature perturbations instead of metric perturbations, also allows you to decouple all of the different curvature scalars. Each of them satisfies a PDE, and that PDE also separates into a bunch of ODEs. So once again, you only need to solve ODEs to be able to solve perturbations of a Kerr black hole. Amazing. All right, so that covers the extreme left-hand side and the extreme right-hand side, and we only need to talk about the middle. So there is where we need to use numerical relativity. And you don't have any symmetries. People have been trying to do this since 1964, amazingly. And it took until 2005 for this to actually work. So I would like to show a movie because it wouldn't be a talk about numerical relativity unless we have this nice visualization. So what you can see here, let me pause this for a second. So we slice up space-time into space and time. We choose a foliation. That's arbitrary, but you can make some gauge choices. And then you turn the Einstein field equations into an initial and boundary value problem, and you try to numerically solve it. And people didn't understand all of the details of how to do this properly for a long time, as you heard. But so now we can do this very regularly. So each of these simulations, depending on resolution, can take, a week or months, or a month, depends on how patient you are, how much CPU time you want to burn. So what you see here is a two-dimensional slice through a three-dimensional slice. So this has color and depth encoding the curvature and the lapse. You see these vectors on the surface. Those are encoding the shift in your 3+1 split. Up at the top, we have some apparent horizons that we find during the simulation. There's some trajectories of the apparent horizons. And at the bottom, you see the waveform that's very far away, what you would see from this binary. So LIGO only sees this bottom part, of course. Okay, so you burn a lot of CPU time, a merger happens, you get a common horizon, then you get a remnant black hole. All right, that was our obligatory numerical relativity visualization. All right, so to put this on the computer, you take these beautiful equations and you make them very ugly, but this is what you need to do to make them amenable to casting as an initial boundary value problem that you can stably evolve. It has a good initial value formulation. There are lots of different ways of solving these equations. Well, I mean, this is not the only formulation. This is the generalized harmonic first order form formulation. You can do others, but in the spec code, that's what we use. We break up space further into a bunch of subdomains, and we use pseudospectral methods. So we have smooth basis functions in each of these subdomains, and we represent all of the data in terms of a decomposition onto these smooth basis functions. So then our spatial derivatives can become exponentially convergent. Okay, great. This is actually, I mean, this is only possible because apparently the binary black hole problem is C infinity outside of the horizons. If there were shocks, then pseudospectral methods would only be polynomially convergent. All right, anyway, so let me talk about the important thing, which is how do we get the waveforms out of these simulations? So I'll talk about the old way first, and then I'll talk about the new way. So I'll explain this, but you don't have to remember it because it's all going to be superseded in a few slides by this Cauchy-characteristic evolution thing. But the old point of view is the following. So we have some finite domain, right? It only goes out to some maximum radius. That's the outer boundary here. And we pick a bunch of coordinate spheres inside our simulation volume. So each of these vertical lines is a coordinate sphere. And we save the strain data on those coordinate surfaces. Then in post-processing, what we can do is we can try to find surfaces that are null, so outgoing null rays going through all of these coordinate spheres. And on those approximate null surfaces, we interpolate the data to a common set of times across all of those different spheres. And then you basically just do a fit in powers of 1 over r to this data. There are a lot of approximations going into here. But this still is the kind of standard way of getting the waveforms out of the simulation volume and approximating what they will be at arbitrary distances, right? So this should sound a little bit like Richardson extrapolation. So you basically use data in the volume to do a fit to powers of 1 over r, and use the fact that if you understand post-Minkowski theory, there's a coordinate system where the strain at very large distances is the power series in powers of 1 over r, exactly like this. Okay, and then the piece that's slowest decaying, just the 1 upon r piece, is the piece that we care about. That's the part that makes it to the detectors.
Is it guaranteed that there are no log R terms? Sometimes when people study asymptotic expansions of flat space,
that's right. Yeah. There absolutely are log R's if you use the wrong coordinate system. That's absolutely true. And so, but if you look back at like Damour and Blanchet, 1986 or something, they go through how to, find the coordinate transformation to get rid of all of the logs. I think that it's also in Bondi, in the Bondi-Metzner-Sachs papers, showing that there's just a power law expansion around Scry. But I don't remember. Okay, so one of the problems with this extrapolation procedure is that it does not seem to resolve memory. And I don't think that there's any deep understanding for why that's the case. But empirically, it seems like you don't get memory out. So here's what I'm talking about. The strain should actually have this memory of the fact that a gravitational wave has passed. And after a gravitational wave passes, your inertial ring of test masses will have some final distortion. It doesn't have to return to the initial shape. You can go from flat space to flat space, a gravitational wave passing by, and start out with a ring of test particles and end up with a deformed ring. And it's still Minkowski space and Minkowski space, but it's not the same coordinates for both Minkowskis. So there's no contradiction there. All right, so the real result of a gravitational wave passing should have this kind of memory. Now, in the old way, it seems that these extrapolated waveforms don't have memory. Well, one thing that you can do is you can say, let me assume that nonlinearities are weak. So let me just post-process these waveforms that don't have memory and insert the memory by using flux balance laws. So these balance laws are essentially just the Bianchi identities. But you can write them in a way to say, what should the memory be? This should be nonlinearly consistent, but then we're not doing any sort of consistent thing. We're basically just adding in this thing. If you're saying nonlinearities are small, let me take the part of the strain that I did get out from this extrapolation procedure and then reprocess it in a way to add back in the memory that should have been there. Again, it's not some self-consistent thing, but it's a good approximation that seems to have worked. But anyway, let me emphasize that this is still the old way to do things. So if this sounds funny, it is, but don't worry about it too much. But if this is something that you want to do, it's implemented in this package called SXS. Or maybe this is in the Scry package. There's another package called Scry. Oops, that's supposed to be a C. I can't write it apparently. It's SCRI, which you can install, which does this memory correction. But actually, we've done this entire memory correction on all of our public waveforms. So if you install this SXS package and you say, get me waveform number 309 or something, then you'll get the waveform that has the memory correction put into it already. All right, so now let me talk about the new way to get the waveforms out of the simulations. And I already mentioned this, there's this Bondi formulation of going to, in asymptotically flat spacetimes, treating the region approaching Scry in a null foliation. And you can write down Einstein's field equations in this null foliation fully nonlinearly and turn that into a set of differential equations that you want to solve. So, okay, maybe these words don't mean anything, so I'll write well, actually, there's something that I should say in words without equations first. So we want to bring infinity into our simulation domain so that we can actually get the waveforms all the way at infinity. We can't do that out to I0, right, to spatial infinity, because if you take a Cauchy surface that goes out to I0, it has an infinite number of cycles of oscillations of the strain approaching I0, so you have an essential singularity at I0. On the other hand, if you approach scry along a null ray, you only have a finite number of oscillations of the strain. So you can compactify your spatial domain with no singularities approaching scry. And you know the asymptotic fall-offs, so you can get finite quantities at infinity. So that when you rewrite the Einstein field equations in this way, you get a system of equations that are hierarchical. You can treat the angular sector fully spectrally, and then you've got basically a bunch of coupled PDEs in the radial and time direction. Yeah, sorry.
Can I ask a question, Leo? So
of course.
These oscillations near I0, so doesn't that depend somehow on the initial data that you took for the simulation?
Yeah, it does.
So,
I was imagining that this binary has existed forever, which I know is not physical, but
forever. Okay.
That's the post-Newtonian thing to assume.
Okay.
Yes.
I
Fine.
see. Okay. Okay, thanks.
Right. I lied a little bit, but anyway. Okay, good. But really the place we want to go is scry, or we assume that we're very close to scry. All right, so these equations, all right, maybe this slide is not very important because seeing the details of these equations is not super useful. You should not try to do this by hand. You should do this in Xtensor, because otherwise you'll make algebraic errors. But there's a very nice structure to the system of equations that you get. So there's a whole bunch of variables that you want to simulate. There's hypersurface equations, and then there's an evolution equation. So you get a whole bunch of equations that are ordinary differential equations in the radial direction, right? So if you have data for J, whatever this J quantity is, it's like strain, then you can integrate this equation to reconstruct beta. And so now you have beta and J, so you have the right-hand side of this equation, and you can integrate it to get Q, and so on and so forth. So you can go through this hierarchy of equations, recovering all of these quantities until you've recovered H, and then H is on the right-hand side of this evolution equation, so you can take a step forward in time, which is U. And then you just solve the system of equations going all the way out to scry. All right, so if you want the actual details of how this works, there's this paper led by Jordan Moxon. And this is implemented in the new code Spectre. So it was previously implemented in Spec, but Spectre is the next generation numerical relativity code. So we can take our Spec simulation data and feed it into this Spectre module to take the data from a finite world tube and integrate it all the way out with the fully nonlinear Einstein field equations all the way out to scry. So I don't want to say too much more, except part of this picture is missing, right? I said we take simulation, a Cauchy simulation world tube, which has some boundary conditions, and then we just use that as initial data for this separate code, the Spectre module. There should really be information flowing in both directions, because you have backscattering from the curvature in the exterior domain. It can backscatter radiation into your Cauchy simulation. This doesn't happen in what's called Cauchy-characteristic evolution with an E. It's just treated as a one-way information flow problem. So the next step in this is called Cauchy-characteristic matching. And you can look at this paper led by Xizhang Ma, who was a grad student at Caltech, now postdoc at the Perimeter Institute. And this actually couples the two evolution systems together. So you get evolution, so you get information flowing back from the null foliation exterior domain back into the Cauchy system. I think I can probably safely skip this. These are just the things that we do in numerics to make sure that we're solving the equations that we think we're solving. So this is checking how well are the Bianchi identities being satisfied. So there's time on the horizontal axis, the error in some quantity on the vertical axis, and the extrapolated data is the dashed. So this is the old technique. You can see that it's making errors. As time goes on, these errors accumulate. And these solid curves are the errors in the Cauchy-characteristic evolution. So those are the solid colored curves. And this dashed black curve is kind of the not self-consistent adding back in procedure that I mentioned before. So this kind of course, this uses the Bianchi identities. So of course it satisfies the Bianchi identities at some level. But that's not really a very useful thing to say because this is like not internally self-consistent. Okay, now, so we have this code in-house, and in the future, we will make all of the public waveforms using either CCE or CCM. We haven't done that yet because putting together one of these big waveform catalogs is a lot of work. So far we have released only this tiny mini catalog of 13 simulations. But if you go to data.blackholes.org and you want to play around with waveforms that actually include memory, where it's actually been resolved, and have all of the Weyl scalars in them, then you can get them from these small set of simulations. And we've done a bunch of different work with this mini catalog of things that you can do now that you can actually get all the way out to scry. Okay, so I've spent 40 minutes talking, and I haven't yet talked about the different BMS frames. I'm finally going to get to that. Are there questions before I start talking about BMS?
Leo, was the old method also blind to long time effects like the price tails, or was it just the memory which was being missed?
So the price tails are extremely difficult to get numerically. And I think even with CCE, we don't see them.
I see. Okay.
They're just so far down in amplitude that we haven't been able to see them. I know there was a recent paper claiming that RIT waveforms have power law tails. I think that's incorrect. Oh, this is being recorded, right? I should be more diplomatic. I think that there are issues that they're not taking into account. It's extremely difficult to resolve these price tails. If you look at what people have done just in perturbation theory, just in linear perturbation theory, it's still very difficult to resolve the tails. And so as far as I'm aware, no full 3+1 nonlinear numerical relativity code has shown that you can actually resolve the tails. And by resolve, I mean, you do the simulation at multiple different resolutions, and then you check that what you're seeing is a real physical thing and not something like, oh, we got our boundary conditions a little bit wrong, and that actually means that you end up with something that looks like a power law tail.
I see. Okay. Thank you.
All right. So BMS. BMS is the symmetry group of future null infinity. We are pretending that we are in an asymptotically flat spacetime and that we live very close to scry. Now, so what are these symmetries? Of course, if it's asymptotically flat, you expect there to be Poincare transformations, but there's actually many more because scry is a null surface. All of these inertial observers on scry can't signal with each other, right? There's the only light rays that they can send out just go along their generators. So they're free to advance and delay their individual clocks arbitrarily. That gives you super translations. Oh, that's what I was trying to demonstrate here. You're free to smoothly change the time function that you choose on scry as a function of angle, not as a function of time, because they have to be affinely parametrized, or their clocks should tick at the same rate. But you're free to choose the one function on the sphere to advance and delay each different null generator by a different amount. Now, if you are an observer, then you're just sitting along one of this green ray that I drew here on Scry. I tried to draw the legs of the LIGO detector. So LIGO doesn't care about this, right? LIGO is only on one of these generators. So this is just changing your origin of the time coordinate where LIGO is recording the data. So this doesn't matter, right? But the problem is that there's the detector problem and there's the modelers problem. So the modelers do care because we have to provide a family of waveforms to the people who do the detections. They're going to do parameter estimation. They're going to try to do Markov chain Monte Carlo in some parameter space. And what they need is a family of waveforms that's smooth as a function of parameters. And the waveforms that we give are functions on all of Scry, not just at a point. Okay, I think that I didn't actually have any words explaining that, but I motivated that we should actually care about BMS in the modeling problem. So BMS includes Poincare transformations and also these super translations. Super translations are just this thing that I said where you can take the time function and choose a global advance or delay that's a function of where you are on the two-sphere. And it does something to the coordinates like this, right? So you can take stereographic coordinates on the sphere, you can do a Mobius transformation of them, and you can also advance and delay the times like this. So if you do this to the coordinates, then you should do a pullback and figure out what happens to the strain that you're trying to model. So what does it do to the strain? So our new strain, let me only do it for a super translation because the rest of it is actually pretty easy. So for the new strain, after we plug in this u minus alpha into the time slot here, if you were to expand this in the first argument, then, first of all, this changes your memory. This gives you an overall offset to the strain as a function of angle. But it also introduces this first term because if you try to expand strain in a bunch of spin-weighted spherical harmonics, then you have to multiply these spherical harmonic modes in H with this angular function. So you multiply two angular functions together and you get what looks like mode mixing. So, we like to compute things in terms of spin-weighted spherical harmonics because it compresses the data. But then when we do one of these BMS transformations, it mixes all of the modes together. So you have to take this into account. These were the words that I said earlier about why do we actually care about BMS. So to make the waveform family smooth in parameter space, you want every one of your simulations, you want every one of your waveforms to be in some well-defined BMS frame, right? You want to gauge fix BMS. But there is no canonical choice. So what choice should we make? So there is a canonical choice if you have a stationary region of Scry. There's no radiation. And the canonical choice that you can make is you can make the mass aspect be isotropic. You can take the angular momentum aspect and make it only have L equals 1 content. And you can align that L equals 1 function with the z-axis, so it's azimuthally symmetric. So morally, what you're doing is you're putting the system into the center of momentum and center of mass frame, and you're saying that there will be no memory in this frame. That's a consequence of going to this canonical choice for stationary regions. Of course, we don't have stationary because we have a binary that's emitting a bunch of gravitational waves. But you can apply this idea, you can motivate this idea to have like two different almost canonical choices. So at very early times or at very late times, you can apply this idea. So at very late times, you can make the remnant black hole be in the center of momentum frame in the center. And at very early times, you could make the center of mass of the binary be in the center of momentum frame and at the center of mass, and make the strain go to 0 as you go to minus infinity. Of course, our simulations start at some finite time, so we can't really achieve this, but we can try. All right, so maybe I'll skip this. This is BMS frame fixing the old way. I'll skip this and say, oh, I do want to show this slide. So this is, you can see this mode mixing thing in the waveforms. So this is why we need to actually fix the BMS frame. So what I'm showing here is, as a function of time, the strain in the 2-1 mode for an equal mass binary with no spins. So in the inset is the 2-2 mode. And what you might notice is that the frequency is the same between these two modes, which is not what post-Newtonian theory predicts. Post-Newtonian theory predicts that this should go as e to the I m phi, where phi is the orbital phase. So m equals 1 and m equals 2 should have frequencies that differ by a factor of 2. So the reason that these are at the same frequency is because the 2-2 mode is huge compared to the 2-1 mode. And because we're in the wrong BMS frame, this is mixing into the 2-1 mode. So this is not agreeing with post-Newtonian theory. So if we do this old thing of fixing the center of mass in a Newtonian way, it fixes 2 orders of magnitude of the problem. But then finally, but the frequency is still wrong. Finally, if you use the new BMS frame fixing procedure, you can see that you get the correct frequency for the 2-1 mode. So you can undo the mixing by going to the correct BMS frame. All right, so the new way, the technical part is not very important. There's some quantity called the Marashi supermomentum, which is some geometric stuff, but the best interpretation I have of this Marashi supermomentum is that if you go to look at the memory part of the strain, defined in a certain way in an appendix of our paper, then it is proportional mode by mode with this thing called the Marashi supermomentum. So in effect, what we do is we say, let's get the post-Newtonian prediction for this quantity called the Marashi supermomentum, and let's find the frame that gets our numerical relativity waveform to agree with this post-Newtonian prediction. So what we're doing, in effect, is making our memory part of the strain agree with the post-Newtonian prediction for the memory at early times. I think I will skip all of this stuff because I'm basically at the end and this stuff is not as important. I will mention something about ringdowns because, there seems to be constant discussions about ringdowns. So ringdown modeling goes back a long ways. And this is what a ringdown should look like. This is what a ringdown does look like. It looks like a damped sinusoid. Notice that the strain is going to 0, although I don't have an axis here. The strain is going to 0 at very late times. That's what you get when you solve the Tucholsky equation, right? The Tucholsky equation admits solutions that are e to the minus I omega t. They look like this. So this solution goes to 0 as as time goes to plus infinity. But where's the memory, right? Our actual numerical relativity waveforms, now that we're using CCE, they have memory. So if you tried to do ring down fitting with this blue waveform on the left, your fit will make a valiant attempt to try to recover the fact that the strain rises up to some asymptotic value, but ultimately it can't do it because there's nothing you can do with a bunch of damped sinusoids to get this constant offset at late times. So instead, what you should do is you should apply a BMS transformation to get yourself into the frame where the strain actually does go to 0 at very late times. And these are clearly different frames. So if you're doing ring down modeling with waveforms that somebody gives you, and they don't tell you what BMS frame they're in, then you're doing it wrong. So even if there's other things that you could try to do. You could try to just subtract a constant from the waveform. And that is actually still worse than getting yourself into the correct BMS frame, of course. So the effect of this BMS transformation is not just adding a constant, there's also mode mixing. So you can see these two different curves. The red curve is CCE changed by a constant in the old frame, and it's doing worse than getting yourself into the new frame. And even more apparent here. Okay. So sorry that I didn't get to talk about these other applications. Yes.
So isn't another way to think about this is the fact that the Cauchy scalars are related to curvature and not the metric itself. And then they should go to 0 at times, but not.
Yeah, that's true. Yes, absolutely.
I mean, it's okay. So, but you are writing the metric perturbation kind of directly as a function of these
yeah,
the curvature
yeah. If you do
scalars.
metric
So
reconstruction
somehow
from
something
those,
is missing there.
right? If you do metric
Right.
reconstruction from the two Cauchy scalars, you get this as well, but there should also be memory terms.
Mm-hmm. Okay, thanks.
Okay, so I guess I wanted to be able to talk about hybridization. This is what we do at very early times because our simulations are only a finite length, and we want to be able to go back arbitrarily far in time. So we want to be able to splice the NR simulations with post-Newtonian predictions. And that can only be done properly if you're in the same BMS frame, right? So post-Newtonian calculations implicitly have been making a BMS frame choice, but they didn't say, here's the choice that we're making. But anyway, so to do this splicing, you have to get in the correct BMS frame. You can see that the 2-0 mode here has memory. It's not at 0, right? So almost all numerical relativity waveforms that you'll find, the 2-0 mode is, well, either missing or it looks like it's oscillating around 0 at early times. Okay, so I'm going to skip all of this because I ran over time. I'll say that we now have a surrogate model which actually incorporates memory coming from CCE waveforms. So this was trained directly on CCE waveforms. So if you do pip install GW surrogate or conda install GW surrogate, then you can get these waveforms that actually include memory without doing an NR simulation, just 10 or 20 milliseconds using this thing called a surrogate model, which I didn't explain. Very sorry about that. All right, but let me wrap up by saying, here's what I think that you should remember. We now have the ability to take our simulation from a finite Cauchy volume and integrate it all the way out to scry, spectrally accurately. We can resolve memory. Now, using this new technology, we've actually been able to exploit it to put in a bunch of details that were missing from modeling in the past. Namely, that if you're doing black hole perturbation theory at late time, doing ringdown modeling, you're doing it wrong unless you're in the correct BMS frame. And at very early times, if you want to combine with post-Newtonian theory, or if you want to provide a smooth family of waveforms to LIGO practitioners who are going to try to do MCMCs against the data, they want a smooth family. They want all of the waveforms to have been in the same BMS frame choice. So post-Newtonian furnishes a BMS frame choice that we can make use of to make this not canonical, but as canonical as we can get BMS frame choice. And I didn't really get to talk about the applications. Very sorry about that, but I can point you to some literature if you're interested. So thanks for your attention, and I'll be happy to take any remaining questions.
All right, thank you for the fantastic talk, Leo. We have plenty of time for questions, so anybody who has one, just unmute yourself. Maybe I'll get it started. Could you maybe say a couple of words about what people think about potentially observing the memory effect, sort of a timeline when it might happen, what's required?
Yeah. So this is something that David Nichols and Alex Grant have done very serious studies about. So predicting how sensitive would next generation ground-based detectors be to being able to see memory. So if you do literature search for Grant and Nichols, then you'll find the predictions, the forecasts. And I think if I remember correctly, they said that the most well-known type of memory, the displacement memory, would be seen within like 3 years at at the proposed sensitivity of next generation detectors. And then there's more subtle memory effects like this thing called the spin memory effect, which I don't remember what they said about whether or not it could be seen. I think maybe you can't just see it directly, but there's this idea of stacking, where what you do is you say, let me take the signal, let me try to improve my signal to noise ratio by taking many, many detections and saying, based on my understanding of spin memory, if I do a rotation to all of these different waveforms in the following way and add them together, then all of their spin memories will constructively interfere, and I'll boost the SNR in the spin memory. So if you stack, then it would be possible to like take 100 or something detections together and see spin memory. But you have to check with the papers. I might be misremembering the numbers.
Okay, thanks. Any other questions?
So maybe, I don't know, it's a kind of a vague question, but about that regime in Kip's cartoon, the middle one that looks very frantic when he drew it, but it turns out to be much smoother.
Yeah.
So what's your intuition about why that happens, and is that related also to the fact that kind of the extreme mass ratio goes more into the numerical relativity part more than you would guess?
Yeah, I think
Then you would
the answer
like
is probably
nail
yes,
it.
that these two are related. And I mean, maybe this question is above my pay grade, because it might be very deep to ask, why is it that this problem seems to be so much, well, I wouldn't say simpler, but the waveforms are generally much simpler. And I guess one of the suggestions is that GR is not very nonlinear, which I don't really know how you can quantify how nonlinear something is. But there was a paper by Abe Hart around, I don't remember, maybe 2014, called The Not So Nonlinear Nature of the Einstein Field Equations, or something along those lines. I mean, I think morally what Abe was trying to get at was that the amount of nonlinearity is not very large. I don't really know how to make that a precise statement. I mean, I think it's interesting. If you go back to what people were doing with numerical relativity simulations before Franz solved the merger problem, there was this Lazarus project, where they would do their inspirals, which would then crash before merger. They would take that data, and then they would prescribe it in a certain way to a Tucholsky solver, to a code that was built on solving the Tucholsky equation. So they would take data from a binary which had not merged yet and try to use it as initial data for, linear perturbation theory on the Kerr background. And this apparently worked. I mean, you don't get fully self-consistent full NR waveforms, but apparently this was possible. I don't understand why either.
You get a good approximation to the final.
Yeah. And so I think, similarly, why is it that the small mass ratio, I mean, okay, this is a different small parameter. It's not like G is small, but still the amount of nonlinearities in GR seem to be not so nonlinear, to the level where apparently doing the small mass ratio expansion also allows you to to agree even at mass ratios up to like 1 to 10. It must be coming from the nonlinearities being not so nonlinear. But anyway, if anybody knows how to make precise the statement, like how do you quantify how nonlinear is this theory, I would love to know.
Well, I mean, like, in mathematical geometry, there is like, this is well known. This is like called the weak null structure in the Einstein equation. So the nonlinearities are not like,
Right, you
like
can't get
that
shocks.
nonlinear. There's like some
Yeah.
cancellation
Right,
going on there.
it's linearly degenerate.
So you can look it up, like the null structure. So you can get all the details there. Like everything is
Yeah.
there, basically. Yeah.
That's right. I don't really have an intuitive understanding of what that means, but
Yeah, I mean, if you write down like the equations in like suitable frames, like let's say double null frame or something, then you don't have concentration of energies, along the vertex of the cone, so to speak.
Right.
You have like the things going out of the cone.
yeah.
Like you have the dispersive effect actually more dominant than like the concentration effect, so to speak.
Mhm.
Yeah, you can look it up in weak null structure, I guess, like Rodniansky Lindblad, like 2002 article, something like that.
Do you have an understanding of whether or not, I mean, like when we do our NR simulations, we have, okay, we don't know where the event horizons are, but we track apparent horizons, right? And so more or less, I'm thinking of like the structure of the null cones near these two apparent horizons. When they're getting very close together, it seems very important. And it would be nice if we could somehow exploit the fact that nonlinearities are not that important to like, be able to, make the simulations easier somehow.
I see. Yeah, that's actually, yeah, that sounds interesting. Yeah, maybe that's what like this actually plays an important role. Yeah. Yeah, let me think about that. Like, yeah, this is actually very interesting. Yeah.
Yeah.
Thank you. This is a really nice talk. I thank you for the talk. Yeah.
All right. Well, if there are no more questions, let me stop the recording. We all thank Leo again for a great talk.